So last week, having previously been looking at very large, quite large cardinals, things like inaccessible cardinals, last week we came down to earth and started looking at sets of real numbers. And in particular, we had two main results. So the one was that every closed set has a so-called perfect subset. We had a few results. I want to focus on two. We had every closed set as a perfect subset, which we defined last week. These closed, non-empty closed points sets that don't have any isolated points. And this we proved. But then I generalized it at the end to a more generally valid statement, which is this is true not just for, every uncountable closed set as a perfect subset. But in fact, we had the notion of the perfect set property, that the set has the perfect set property if it is either countable or it contains a perfect subset. So let's state this as rather every closed set has the perfect set property. And then we stated a more general result that this actually applies to not just to closed sets, but to Borel sets, which many of you have studied in measure theory, for example. But it's a much broader collection of sets. So this is just stated. And while we address these for the real numbers, so this holds for sets of real numbers. So in other words, the subsets of R. It also holds more generally for subsets of any Polish space, a concept which we introduced last week. The subsets of Polish. And you'll remember Polish space was a topological space whose topology is given by a metric, and that metric has to be complete and also separable, so that there exists countable dense subset. And one important Polish space is the space of real numbers. And another important Polish space that I mentioned last week is going to play a more prominent role today, so I want to remind you of it, is the space that's known as bare space. So an important space. Bare space. And this is its underlying set is the space of infinite sequences of natural numbers, or if we like, total functions from natural numbers. And the metric, which I introduced this last week, is given by one infinite sequence S. The distance between one infinite sequence S and another one S prime is, of course, 0 if S is S prime. And otherwise, in the case that they're not equal, we give the distance as 1 over 2 to the n, so 2 to the minus n, if n is the smallest number at which S and S prime disagree. So if n is the least number, such that S of n is not equal to S of n prime. And I invited you last week to think about this topological space and try to get a bit familiar with it. It's going to come up very importantly later today, and we'll try and get a bit of intuition when we do. But the most important thing we're going to need to understand here, which is not very complicated, is how what Cauchy sequences look like in this space. So we'll leave that to wait until later. I just want to make two remarks about this space, one of which I made last week. So firstly, the space infinite sequences like this is the remark I made last week. It's homeomorphic, so isomorphic is a topological space to the subset of irrational numbers, irrational real numbers with the subset topology. So I use the isomorphism symbol. So it's homeomorphic to the space of real numbers with the rationals removed. You can think about, I've asked you to think about that for yourselves last week. If you haven't already done so, the notes today include an explicit description of the homeomorphism. So that's one remark. And another remark for those who know some topology. Real numbers is a very nice space. It has a lot of good properties. It's active, for example. It's locally compact. Their space is not locally compact. And that's because of that, it's in many ways quite an awkward space to work with topologically. But in terms of viewed as a metric space, and if we're interested in Cauchy sequences and their convergence, it's actually not hard to deal with. But anyway, the remark is that it's not even locally compact. And if you're not very familiar with point set topology, then never mind about that. Okay.
Something that should be S prime.
That should be S prime of n, not S of n prime. Okay. Yeah. Indeed. Very good. Okay, so we've got a main topic for today. Thus, we're not going to get onto that topic for a little bit. So as a warm-up, I want to continue in the direction that we were going in last week. So we showed every closed set has the perfect set property. I stated that every Borel set has the perfect set property. Maybe every set of reals has the perfect set property. And I think I already stated last week that if every set of reals has the perfect set property, then the continuum hypothesis holds. So that's in the notes for this week, but it's very simple because the perfect set property says, we've got a set, if the set has a perfect set property, then it is either countable or it contains a perfect subset. It's countable. It's countable if it contains a perfect subset. Well, we saw last week that perfect sets have cardinality for continuum. So if a set has the perfect set property, then it's either countable or has cardinality for continuum, or it has a subset that has cardinality for continuum. So if every subset of the reals had the perfect set property, then every subset of the reals would either be countable or have cardinality continuum, namely the continuum hypothesis result. So that should make us suspicious. We're not going to be able to prove that every set has the perfect subset property, but can we provide a counterexample? Can we find a set of reals that does not have the perfect set property? And we can, but we need to use the axiom of choice. That's one of these properties that that every set of reals having the perfect subset, having the perfect set property is actually consistent with the negation of the axiom of choice. But we have the axiom of choice. So for today's lecture, like last week, I'm not going to take the axiom of choice as as basic. We'll have dependent choice, but we're going to have some results that do depend on choice, like this one. And when we have such results, I shall flag the use of the axiom of choice. So the first, I think it's in the notes, it's theorem 2 because proposition, or theorem B, because proposition 1. Let me check how I'm numbering them. Yeah, theorem B, because proposition 1 was the statement that if every set has the perfect subset property, has the perfect set property, then the continuum hypothesis holds. The theorem B, with the axiom of choice, which requires the axiom of choice, says there exists a set, there exists some subset reals. Let me just be consistent with my note. That does not have a perfect subset. In fact, we'll phrase that as there exists an uncountable subset of real numbers such that that does not have a vector. Okay. It's not that hard to prove this with the axiom of choice. So firstly, how many perfect sets of real numbers are there? Well, there are at least 2 to the aleph 0, because every set of the form minus infinity a, or that should be, or it could take a to infinity, it doesn't matter, but every set of this form, every real number a is perfect, and there are 2 to the aleph 0 many numbers a, we can assume so there are at least 2 to the aleph 0 many perfect sets. But every perfect set is closed, and closed sets are complements of open sets, and it's easy, and I think you've done this before in exercises, that there are only 2 to the aleph. Well, in fact, we did last week that there are only 2 to the aleph 0 many Borel sets. So, so the perfect sets are in particular closed, and so in particular Borel. So there are at most 2 to the aleph 0 many of them. So we start off with there are 2 to the aleph 0 many perfect sets. So using the axiom of choice, 2 to the aleph 0 is an aleph. So it's an initial ordinal. So we can enumerate them indexed by ordinal. So we can enumerate, and what letter do I use? So we can enumerate all perfect sets by P alpha. Well, there are 2 to the aleph 0 many, so we need ordinals alpha strictly less than the initial ordinal that is 2 to the aleph 0. Now this is treating 2 to the aleph 0 as an initial one. Now, okay. And what we're going to do is we're simply going to, from every perfect set, we're going to go through the P alphas, and we're going to build up a family of subsets. We're going to build up a subset of the real numbers that does not have a perfect subset. And by doing that, we're going to go through the perfect sets and take 2 members from each perfect set, put one of them into the set A that we're building up, and put another one into a set B that we're going to ensure is disjoint from the set A that we're building up. And so in the end, if we put for every perfect set, if we put one element of the perfect set in set B, which is going to be disjoint from the set we're building up, the set A that we get at the end cannot contain a perfect set, because if it contained a perfect set, it would in particular contain the element of that perfect set that we put in the set B that is disjoint. In other words, we proceed by transfinite recursion. So we define A0 and B0 to be the empty set, and for aleph plus 1, well, the process for defining A aleph plus 1 and B aleph plus 1, given that we've got A alpha and B alpha, we're going to ensure these sets are disjoint, is we choose some little A sub alpha plus 1, no, we'll call it A sub alpha, and B sub alpha in the perfect set B sub alpha, which these two are not equal, making sure that these don't come from the union of the A and B sets that we built up so far. So they don't, so in other words, making sure that A alpha and B alpha are different from any elements we've already chosen to put in the A and B sets. We're going to be able to do that because we're going to make sure the A and the B sets are always going to have cardinality. So A alpha will always have the cardinality of alpha, and alpha is always going to be less than 2 to the aleph 0, so it will always have cardinality smaller than 2 to the aleph 0. Because P is perfect, it has cardinality 2 to the aleph 0. So there are, if we take a smaller set away, there is still cardinality 2 to the aleph 0, many elements left over, so we can take 2 of them and use them for little a and little b. Sorry? No, because we're choosing yes, we should. Thank you. Yeah, because we don't want to choose what we had in the past. Yeah, correct. And A lambda and B lambda, the limit ordinal is the union of all this time, strictly less than alpha of A alpha and B. All right, I still didn't finish defining what of course, I didn't actually finish the definition of A alpha plus 1 and B alpha plus 1, but having chosen A alpha and B alpha, guess what we do? We put little a alpha in, we make A, capital A alpha plus 1, capital A alpha, and add little a alpha to it, and we add little b alpha to B alpha plus 1. So let's continue that part here. So A alpha, so then we have A alpha plus 1 is A alpha union the set A alpha that we had before, union this element we've chosen to not lie in the capital A alpha and the capital B alpha, and B alpha plus 1 is B alpha. Yeah, little b. So one needs to prove that this is a good definition. We're also choosing here, but that's okay. We've got the axiom of choice, and which allows us to. We could just put a well ordering on set and just choose the smallest ones according to the well ordering. So the choice here was okay. And we proved by transfinite induction that it's part of the process of showing it's a good definition. I think I do need some more space. Prove transfinite induction. That the sets are always disjoint. Sorry, that equals the empty set, the intersection, and that the cardinality of the set is always the same as the cardinality of the ordinal that they're indexing, which is kind of obvious because at each alpha we're throwing in a new element. And then, once the definition, so this property is what makes the second part of the definition defined, that guarantees that we can always find these two distinct elements, little a alpha and little b alpha. And then, having done this, we simply define the end A be the union over all alpha less than 2 to the power of 0 of A alpha. And clearly, we could take A or we could equally well take B, doesn't really matter. Clearly, it has no perfect subset because every perfect set will be of the form P alpha, and then little b alpha will belong to P alpha, and little b alpha will belong to the perfect subset P alpha, and little b alpha is not in A. Okay, so A does not contain any perfect subset because for any alpha less than 2 to the power of 0, little b alpha belongs to perfect. The alpha's P subset, the alpha index perfect subset, but the alpha not contained. Okay, good. So there are sets that have no subset as long as one accepts the axiom of choice. Okay. So for today, as I said, we don't want to take the axiom of choice as basic. But later on, I'll flag other things that rely on the axiom of choice. And now what we're going to do, we're going to still for the moment stick with the theme of perfect set. We're going to find another way of exploring. So now we see that it's a somewhat subtle property, whether or not a set enjoys the perfect subset, the perfect set property. That is, it's either countable or it contains a perfect subset. Not every set, because of this, enjoys the perfect set property if we have the axiom of choice. So, how can we explore whether or not a set enjoys the perfect set property? So one tool for doing this is to use a notion of game to test this property. Now, maybe you might feel I'm spending an unnecessarily long time on the perfect set property because maybe these perfect sets are not so exciting after all. One of the reasons for doing this is to use this as a vehicle for introducing games that follow. So these games are very important in set theory and have a lot of applications. But the game I'm going to tell you about now is tailored around perfect sets, and it's a good game to introduce because it's like a simple. The applications of these games are very far-reaching, but the games get quite complicated. And the game for a perfect set, however, is still a bit complicated, but not particularly complicated. So it's something we can do at the level of this course. And now, having got this far with perfect sets, I'm going to use it as a perfect sets as an introduction to this notion of game. The idea is we're going to look at kind of game that we can use for testing or not whether sets enjoy interesting set theoretic properties. So one example is the perfect set property. Another example is whether or not a set is a vague measurable. Those become some measure theory. Another example is whether or not a set is of first or second category in the sense of their category theorem, but anyone who's come across that thing. But as you might imagine, those concepts I'm talking about vague measurability and being the first and second category, these are a bit more complicated. So, as I said, the perfect subset property turns out to be a quite amenable property for looking at these kind of games. But the general notion of game we're going to look at, and it's very important, and it's called and this is the title of today's lecture, so it's called the Gale-Stewart game. And we're going to have some general definition of Gale-Stewart games and some general theory about them. But what I want to do, rather than starting with the general definitions, is start with a particular game so that we can get. And so the idea is to try and get an intuition for how these games are working in a particular example. And then, having done that, it'll be easier to understand the general definition because we'll have something to relate them to. So that's my hope. I haven't always structured it like this in the past, but we'll see if this approach works. So the Gale-Stewart games will come, the general definition will come later. So instead, our introduction is going to be a perfect subset game, perfect set game, rather. And one thing about this game, so it's going to be very specific because it's to do with perfect sets. One thing about this game is when you see the general definition of Gale-Stewart games, it's not going to be totally obvious that the perfect set game is actually a Gale-Stewart game, because I'm not going to define it in exactly the same sense. Gale-Stewart games is going to be working with spare space that I talked about at the start of the lecture. The perfect set game, we don't need to talk about that space to talk about it, so I'm going to define it just in the specific terms that are appropriate. In the exercise class next week, you will see in what set that the perfect set game is actually a Gale-Stewart game. It's not that hard to do that. This is something you can think about in your own time before the exercise class next week. So anyway, we're going to look at the perfect set game, and it's going to be, even though I'm not going to present it directly as a Gale-Stewart game, it's going to share some common properties. The most important one is that we're talking about two-player games where the two players play against each other, and at the end of the game, one player wins and the other player loses. Okay, so we have a two-player game. So we're going to player. We're going to use Roman numerals for it. So player 1 and Roman 2. And it's a turn-based game. Player 1 plays first, then player 2. And then player one plays again, player two plays again, and so on. And it's a game of perfect information in that both players see the moves of their predecessors and they know what the current state of the game is. And I don't know how much general game theory you've done, but what will probably be different about these games from maybe any other games you've ever seen before is that these games are going to be played over an infinite amount of time. So player one plays, player two plays, player one plays, player two plays, and you carry on through the infinite time of the natural numbers. Okay, so the first, and the way this particular game is going to be played is at any point in time, so our time is going to be indexed by the natural numbers. At any point in time, we're going to have the current state of the game, and the current state of the game will be a closed interval of real numbers. So we start, and I'm going to use A indexed by n, which is the time. So we start in the state A0, because we start at time 0, and A0 is defined to be the whole of the set of real numbers. Ah. I'm going to rub that off because actually, to begin with, before we start playing, we need to have a goal. And the goal is going to be given by a set of real numbers. And we start with a given goal set. So this is just a set of real numbers. And you know, this is going to, depending on what this set is, this is going to influence how the two players play. And then, based on this set, the associated game which we call the perfect set game of X, because it's determined by the goal set X, is defined as follows. Well, let's just say it's carried out as follows. Played follows. Played as follows. So as I say, at any point in time, we're going to have an associated state, A sub n, hence the time index, which is a set of real numbers. So the game starts in the state A0 defined to be the set of all real numbers. And now the players are going to take turns narrowing down the set A0, the smaller and smaller set. And in the end, we narrow it down. And in the end, we look at, over an infinite plane, we look at the intersection of all the sets that we've narrowed it down through the play. And the way the game's going to be defined, that intersection is guaranteed to be a single. And player one's goal is to get that singleton to be the element in that singleton to be an element of the set X. So that player one is trying to get into is trying to land in the set X, and player two is trying to avoid the set X. But they have rather specific moves they can do to get into and avoid the set X. So on move N, on round, so a round consists of a play a player one and then play a player two in response to player one. So on round n rating equals 1, player one chooses 4 rational numbers. Let me see what they call them. So P, Q, P prime, and R prime, and Q prime, which are ascending. These are rational numbers. Such that the interval P Q prime is contained in A sub n minus 1. So the whole of what's going on is inside the current state that we're in, which is always an interval, which is always an interval of real numbers. And these two intervals here go down in size rather rapidly. So, the size of the interval, the largest size of the interval Q minus between P and Q and between P prime and Q prime needs to be less than 1 over 2 to the n. So the mass of Q minus P and Q prime minus P prime is less than 1 over 2 to the n. That's because I haven't forgotten anything. Okay. And that's layer one's move. And the idea is that layer one is selecting, is giving player two a choice of 2 intervals, either the interval from P to Q or the interval from P prime to Q prime to continue playing it. Then player two chooses one of those 2. So having seen player one's move, two then responds by choosing just a binary digit. Right, so we're choosing 0 or 1. And then we define this determines that the new set A of n is defined to be if 2 chooses 0, then player 2 is choosing the left-hand interval, and if 2 chooses 1, then player 2 is choosing the right-hand interval. So AN becomes PQ if 2 chooses 0, and P prime Q prime if 2 chooses 1. And that's round n. And then, of course, having done that, we now have a new AN that we can use as the start for round n plus 1. And again, player 1 is going to choose now 4 rationals that lie inside A sub n, and player 2 will choose one of the 2 intervals that player 1 is thereby offering the choice of, and the play will carry on like that. So, yeah.
Sorry. Here, in the first step, it doesn't really matter because R is unbound. But then one choose a boundary point for both.
Yeah, one can choose the boundary point. So P, the little p can be. And at the end of play, so the end of the play is at time omega. So at time omega, so after infinitely many steps, is alternation between the two players, and it gives us a sequence A0, A1, A2, A3, A4, a nested sequence of closed intervals where from A1 onwards, the length of the closed interval is less than 1/2 to the n. So the intervals are going down in size. So after infinitely many steps, we have player 1 wins if, well, as I say, if we intersect all the A sub n's, because they're non-empty closed intervals of size at most 1/2 to the n, the intersection is a singleton. So we can define x, little x, to be the element in that singleton. We have that little x belongs to the goal set x. And player 2 wins if little x does not belong to the goal set. Okay. And what we want to do is explain really the next task is that we've got this notion of infinite game, but to explain the mechanics of the game and to see how this thing starts to go. Because it's almost 3 o'clock, so it seems like a good point to have a break. Might as well break it to 4:15. So we're going into that afterwards. Are there any questions on?
Sorry, you might have not shown the okay. Why is this work? If player 1 only wins if this is.
Right, so one way of seeing it's non-empty because from n equals 1 onwards, the sets are all non-empty and compact. Okay, so the intersection actually is non-empty. Then because the width of the sets is, as you go down, is always less than 1/2 to the n. It can't be. Yeah, it's a closed.
I forgot about that part.
Yeah. So you can show the distance. If you have 2 points in this set, the distance between them would be less than 1/2 to the n for every n. So, yeah, good. Right. So we'll have the break. Okay, so we've got this game here. Essentially, in each round, we start off in the current state, which is a closed interval, non-empty. Closed interval with non-empty interior, and then player 1 picks out 2 disjoint those subintervals, and player 2 chooses between. Essentially, that's what's going on, but also the 2 disjoint subintervals are required to go down in size at a prescribed speed. So hopefully, just that picture of having disjoint intervals and then splitting them into more disjoint intervals reminds you of the construction of the Cantor set from last week. So there's some hint of a connection with perfect sets from that. But what is the precise connection between the game and perfect set property? It turns out there's a very precise connection. And this connection is to do with the notion of, so we've got a class of games in which the perfect information games, and the players are alternating, knowing what the players of the other player has done that previous move. And as might have encountered in other forms of game theory, there's then the notion of a player having strategy with which they can use to play the game. And it's going to be very important that the notion of a winning strategy. So a player, I won't write it down at this point because I have a formal definition later when we get to Gale-Stewart games. The informal notion of a winning strategy is fairly clear, which is player one has a winning strategy if they have some approach to choosing what they do at each stage, but no matter what player two responds with, player one will end up winning the game. That's the winning strategy because irrespective of player two's responses, it's going to end with a win player one. And correspondingly, player two has a winning strategy if irrespective of player one's choices, it will end up winning player two. And it's very clear that it can't be the case that both players have winning strategies for the same game, because if you play the two strategies against each other, well, only one of the players will end up winning the game, and so whichever one didn't win the game, that wasn't a winning strategy. So it can't be the case that both players have winning strategy. So what holds for this game is there's a very close connection between winning strategies and the perfect set quantity. And so this is actually a fairly substantial theorem. It's not an interesting general theorem because it's about a very specific game, but it is a relatively interesting game. So it's interesting because it's about a specific game. And it's also interesting because it's illustrative of the sort of subtleties that arise in certain strategies. So the theorem is so let X be a subset of the reals. Any arbitrary subset. And so we consider the game perf of X, which is this game. This is the game, the perfect subset game for X. So the first point is going to be that if X has a perfect subset, then player one has a winning strategy. But actually, it's more than that. Player one has a winning strategy if and only if the X has a perfect subset. So as a winning strategy, so we consider the game for X. We're talking about winning strategies for this game. If player one has a winning strategy if and only if X has a perfect subset. And what about player two? Player two has a winning strategy if and only if X is countable. There's an interesting question about these games, which is, given a game, is it the case that at least one of the players has, well, at least one, if it's at least one, it's exactly one, but is it the case that one of the players has winning strategy? And in such a case, we say that a game is determined. It's determined in the sense that if whichever player has a winning strategy, if they know their strategy, then the outcome of the game is determined from the start. So no point playing it. And that's a common thing in finite game theory. If you have finite games of perfect information that that don't have draws, so guaranteed to result in a win or a loss for one of the players, then there's a standard argument that in any such game, one of the players has a winning strategy. So such games are determined. There's no point playing them from the start if you know the strategy. So there are examples, a famous example of such a game is the game called Hex, a board game called Hex, for example, which results in a win but always results in a win for one of the players. The first player can be proved has a winning strategy, so the game is determined that there would be no point playing the game if the strategy were known, but in that case, we don't really know how to compute the strategy. So people do enjoy playing the game. I mean, these are not the kind of games you can enjoy playing because you have to have a lot of time to play these games. But nonetheless, it makes sense to talk about the games being determined. And so we say, well, I won't write the definition on the board because we'll come to it later in the case of the Gale-Stewart games. So the game is determined if one player has the winning strategy, and notice then, so notice there exists that text such that perfect set game is not determined. Why is that? Because the game is determined by 1 and 2 here. The game is determined if and only if X has the perfect set property. If and only if it's either countable or it has a perfect subset. And we've seen earlier, the first result today, that not every set has the perfect set property. But of course, this relies on the absolute chance. Okay, so I do actually want to get you familiar with how these games work. It's going to get a little bit technical, but I do actually want to prove this theorem in as much detail as we can do without having really formal definitions. So you can just remember the game. But there are 2 if and only if statements. That means we've got 4 implications to prove. 3 of them are rather routine, and 1 of them is quite subtle. And the quite subtle one is the left to right implication of the second statement. That if player 2 has a winning strategy, then set is countable. So we'll leave that one till last. And I think in both cases, the right to left directions are easier. So let's do the proof. I won't bother writing proof, but we'll do the proof of statement 1, the right to left implication. So suppose X has a perfect subset. So we want to define a winning strategy for player 1. So player 1 plays as follows. So given an minus 1, so that's we're playing round n, n greater than or equal to 1. And so at the starting point, we've got n minus 1. And we need to say what player 1 will do on the current situation, n minus 1. So actually, what we're going to do is we're going to maintain as we go along also another set, which is a subset of an minus 1, which is perfect. Okay, so So suppose P0 is the initial perfect subset, which is a perfect subset of R. And we're now at round n by the induction hypothesis. So we're in the case that, n is 1, A0 is the whole of the reals, and P0 is perfect set we've got. But in general, this will be a perfect subset of A n minus 1. Then we had these lemmas for manipulating perfect subsets last week that said, if we take any real number such that there's some element in the perfect set above the real number, then we can bound the perfect set at the real number either by including that bound or excluding it. And we used that in the proof of what was, I think, theorem 3 last week, to basically, if we've got a perfect subset, to always be able to refine it into two disjoint, separated, smaller perfect subsets. So I won't go into the details of such things again, but using properties from last week, we find a P less than Q less than P prime less than Q prime, such that, in the notes I wrote this quite efficiently, so if I do it from my head, it won't come out quite so efficiently. Yeah, so we find we've got a perfect subset in AN, but just as we did in the proof of theorem 3 last week, if we've got a perfect subset, we can find two disjoint parts of that set that both contain perfect subset. You always find a kind of version of the Cantor set within the perfect set. So such that PQ contains a perfect subset L, which is a subset of the perfect subset we're currently working with, and P prime Q prime contains another perfect subset which we'll call R, also perfect subset of the one that we're currently working with. And both these have the relevant size. And Q minus P and Q prime minus P prime. Sorry, I don't need to put in size modulus bars down. We don't need that because the order of them, so those are both less than 1/2 to the n. And then we let player 2 make its choice. Doesn't matter. And this is already determined. Strategy is just what player 1 does. But then, if player 2 chooses 0, we define then we set Pn, the new perfect set that we're dealing with, as a subset of our current An. That's defined to be L, and otherwise we define it to be 0. Right. And we need to show that's a winning strategy. But it's clearly a winning strategy. Maybe I'll go on to the other boards. So player 2 does what they do, and then we keep on going. Somehow the picture is kind of like this, that we're at AN. We've got some we're in round n, and we've got some interval an, and within that interval, there's some green perfect subset in there. And then player one and partitions this. You need to make things small enough that you need to keep enough of a perfect subset here and enough of a perfect subset here. So if you partition it appropriately, but you still have some perfect subsets of the green bits of it's Pn. Now we so this we make this n minus one, and this is an. And then here we've got in green, we've got Pn minus one, and here we've got Pn. And by these sets are always getting smaller, and because we started off with that, we started off with the perfect subset P0, which is a subset of X. So I should have said of X at the beginning, but it does say that suppose X has a perfect subset. These green bits are always subsets of X. So it's clear that player one wins because we've got the play will take us down. So that's not AN yet, but after player two is chosen, so player two might choose the left-hand one, and then after player two is chosen, we then get AN and PN. And because we always have a perfect subset of our interval that's contained in the original perfect subset, which is contained in X, it's clear that the intersection as we go down is going to land in the original perfect subset, is going to land, which is going to land in X. So it's clear that player one wins because the intersection of the ANs is the same as the intersection of the PNs. That's a subset of X. And this holds because we're again intersecting non-empty compact sets. So the intersection is non-empty, but then it's a non-empty set, and so this intersection is non-empty. It's a non-empty set, so it equals this intersection. Okay, right. So that's one implication. So maybe I shall skip the left to right implication of this, which is that if player one has a winning strategy, then X contains a perfect subset, because that is also very closely related to these lengths of that perfect section last week. And we'll just do the third and fourth. Well, the second step, if and only if, the third and fourth implication. So the third one is easiest. That's that if so we're now proving two, and we want to do again the right to left implication. So the right to left implication here is that if X is countable, then player two has winning strategy. So suppose X is countable. So in other words, assuming X is not empty, the empty case is trivial. So suppose X is countable, then we have that X is X1, X2, X3, x4 where we might allow repetitions, because it could be a finite set. And we now need to give a strategy for player 2. The player 2 strategy has the following winning strategy. So at round n, given player 1's move, which is going to be some p less than q less than p prime less than r prime, q prime, or some choice of 4 rational numbers. So it's very obvious what we do. We want to, player 2 wants to avoid the play choosing an element, the infinite play choosing one of the elements in this set X. And so at round n, it just makes sure that it's going to exclude the element xn from the set of possible outcomes that we get from the infinite play. And then over the rounds, we end up excluding, over the infinite number of rounds, we end up excluding the whole of the set. So player 2 simply chooses 0 if x sub n is not a member of the interval PQ. So if it chooses 0, it's saying we're going to go ahead with our next A of n is going to be the interval PQ. And we want to make sure that that doesn't contain the element little xn, so we can choose PQ. So we choose PQ by choosing 0 if xn doesn't belong. Otherwise, we choose 1. Because if xn does belong to PQ, then it's safe to choose 1 because P prime Q prime is disjoint from PQ, and so x sub n can't belong to prime Q. Okay, so that's an obvious winning strategy. By stage at the end of round n, player 2 has excluded all the elements x1, x2 up to xn from the set. And so by the end of the play, all the elements from set X have been excluded. Right, so we now get to the tricky one, which is the left to right implication statement 2. So we want to show that if player 2 has a winning strategy, so player 2 can then force the play to avoid the set X. That's what it means for player 2 to have a winning strategy. Then the player 2 can only do that force if the set X is countable. So it really doesn't have any other kind of clever ways of getting into avoid sets other than excluding countably many options. So let's suppose 2 has a winning strategy. And we want to show the required to prove RTP that X is countable. Right, so to do this, we're going to try to defeat player 2's strategy. Of course, we can't defeat it because player 2 has a winning strategy. But we're going to try as hard as we can to defeat player 2's winning strategy. And that will give us enough information to say, well, if we try as hard as we can, there are only countably many elements on which player 2 can stop us from winning, basically going through the argument. So trying as hard as we can, So what we're going to do is we're going to pick, so we've got the set X, which player 2 is trying to avoid. We'll try and pick some, if player, let's hope that player 2's winning strategy doesn't work. We want to pick some fortuitously good element little x and try to defeat player 2's winning strategy by forcing the play down to that element little x. So let x be arbitrary, little x be arbitrary. We're going to try to force the play. So player 1 is going to try to force the play to act. Player 1 tries to force the play to end up identifying the singleton x as the intersection of all the approximating sets, A sub n. So as follows. So assuming we're still in play, assuming that player 2 has not thwarted us, has not got rid of the element x, assuming we're still in play, so assuming we're at round n, we've still got our element x in a n minus 1. How are we going to play as player 1? Well, we want to try to choose some move so that we will still have x left after player 2's response to our move. So we're going to make a move, player 2, so we split into 2 intervals. We split an minus 1 into 2 intervals. Player 2 will choose one of those. Player 2 has a strategy that it's playing, which is its winning strategy. And we're trying to get to narrow down to the element x. So let's try and pick a move to which player 2 will respond by still giving us our element x available. So if possible, if it exists, we choose p less than q less than p prime less than q prime. Let's call it sub n, because it's on round n, such that after player 2's response, we still have that x belongs to a sub n. Okay, so player 2 doesn't know what we're trying to do, and so it doesn't prevent us because player's got its strategy. This is winning. I mean, in the end, player 2 is going to win, so it doesn't matter. But anyway, player 2 doesn't know what we're trying to do, and player 2 with its strategy allows us to hang on to the myth that we might eventually narrow down the element x. So if that's possible, we do that. Otherwise, we give up. Give up on x. And we say we give up on x and we're going to say all the moves we made in order to say where we were. So at position, what's happened in player 2 might be basing their strategy on all the moves that have been made beforehand. So the position that player 2 is basing what they're doing on is all our moves. So the information it's got is all our moves. So our moves would be, our first move is PQ, P prime, Q prime. Let's call them, let's index them by 1, so that's the first move, all the way up to our last move has been, in this case, Pn minus 1 less than Q n minus 1 less than P prime n minus 1 less than Q prime. But the point is we've had a sequence of moves we've made so far, and at this point, player 2 has finally chosen the interval that doesn't contain action, and we've given up. But for as long as possible, whenever there is one possibility to which player 2 will respond, we choose such a possibility. But because player 2's strategy is winning, eventually we're going to, if player 2 never forced us to give up, we'd play an infinite play in which we kept X in the interval, and in the end player 1 would win, not player 2. So eventually we have to give up. Eventually we give up on X. At some position. Okay. Now we're trying to be really foxy here in how we're playing, because we're basing our choice on knowledge of what player 2's strategy is going to be, because if there is some move we can make that player 2 will keep X in the intervals, we make such a move. We only give up if there's no possible move we can make for which player 2 will keep the element X in the interval. And that's crucial to the next part of the argument, because so every little X in the set X we give up on at some position of our play. But we now note that there's only one element X we can give up on in any one particular position. Because suppose we give up on X and Y at position, well, let's call these are our moves, so we'll call it M1 up to N minus 1. So positions made from our moves, M1 up to N minus 1. Well, that means that there is no move we can make in which after players 2, so this means that both X and Y are contained in A N minus 1, because that's what we were assuming in order to be, that's what we're maintaining in this way of trying to narrow down the elements. And it means that because we're giving up, it means that whatever player 2 responds, neither X nor Y will be in the resulting set after player 2's choice. But then we simply choose some. So suppose, without loss of generality, X is less than Y. We simply choose P n less than Q n less than P prime n less than Q prime n, such that X is contained in the interval Pn Qn, and Y is contained in the interval P prime n Q prime n. We can certainly do that, because what X is less than Y, we just need to choose two sufficiently small intervals to satisfy the size requirement. But now player 2 has to choose one of these two sets, and therefore will not have eliminated one of X or Y. And we were saying that we were giving up because we only give up if whatever player 2 if every response, the response of player 2 to every move we make ends up eliminating that element. So that's the contradiction. So one of X and Y not eliminated. That's if X is less than Y, and similarly if Y is less than X. In other words, so we can't give up on two distinct X and Y. So in other words, we give up on, at any position in our play, we can give up on at most one element. So for any position in our play, we give up on at most one element of X. But also, as we said, argued at the beginning, every element of the set X, for every element of the set X, there is some position at which we give up on it, otherwise we would be able to win a play with that value. So for every element of X, there exists a position on which we give up. We give up on little x. And lastly, we observe that our positions are just finite sequences of four tuples of rational numbers, so there are only countably many positions. So every element of X is assigned to each of the countably many positions determines at most one element of X, and every element of X is determined by one such position. So there are at most countably many elements of X. Well, there are countably many of X. So there are. So X is countable. X is therefore countable because there are only countably many positions. Okay, so it's quite a subtle argument, but anyway, a nice one. Right, so that is enough on the perfect set game. So now we come to the main topic of today. We're almost into the third hour already, but we can finally do a Gale-Stewart game, and now it's quite easy to understand. So Gale-Stewart games are just a general setting for these infinite prime two-player games. So, the Gale-Stewart game so players 1 and 2 take it in turns to make moves, but the moves are just choosing a natural number. Players 1 and 2 take turns to choose a natural number. So the perfect set game, we weren't just choosing natural numbers, but our choices were being made from countable sets, like the rationals, so they can be coded as choosing natural numbers. So that game can be coded as choosing natural numbers. So we tend to write a game like this. You can just think of a play as just a sequence, which in the notes I start with 0, so let's start with 0. So player 1 chooses the natural number n0. Player 2 responds. Sees player 1's move, responds with a number n1. Player 1 then responds with a number n2, n3, n4, and so on, n5. And the game is simply determined by a goal set. Well, determined is the wrong word because determined means one player has a winning strategy. The game is specified. The game is given by specifying a goal set, which is simply a subset of, well, a play is an infinite sequence, so it's going to be a set of infinite sequence. So this is where their space is going to come in, because our goal sets are now going to be subsets of their space. And the play, which is these infinite sequence of numbers, the player one wins the play, which we'll just use an infinite sequence of numbers, written like that, if that infinite sequence belongs to the goal set. And player two, so the goal set is player one is trying to get the sequence of numbers to belong to this set, and player two is trying to avoid the sequence of numbers belonging to this set. Player two wins the play if the infinite sequence of numbers is not belong. Okay, so looking at the perfect set game, we can view the perfect set game as picking a sequence of numbers, because the moves of player one, P, Q, P prime, Q prime, these ordered things, they countably many moves, so we can encode them as natural numbers. The moves of player two are just 0, 1, so we can certainly encode that as natural numbers.
Sorry,
But yeah.
just from for
No, sorry, it wins a particular play, that's a particular sequence. So the play, the play is the two of us have sat down.
yeah, okay.
I'm player one, you're player two. We've sat down and we've played for an infinite amount of time and we fixed a particular sequence.
Yeah,
So a play is a particular sequence, and I win that play if I manage to get the sequence in.
The whole sequence then.
If the whole sequence. So I'm viewing this as a function.
Yeah.
So this is a set of of functions, which is the same as a set of infinite sequences. So the whole sequence is in the set, and
In essence, there.
okay. Sorry, the notation. Yeah, so this is, so if you like, this is function I map to the ends of play. Okay, so now let's talk about the perfect set game. So the perfect set game, we can certainly view the choices as natural numbers. There's another issue there, that in this game, the Gale-Stewart game, there are no rules. In the sense, all you need to do is pick a number. There's nothing else you need to do. Whereas we had some rules in the perfect set game. We had rules that you're not just choosing a P, Q, P prime, Q prime, but they need to be in a certain order. Moreover, the two intervals needed to be a certain length and this kind of thing. So in order to encode the perfect set game as a Gale-Stewart game, it keeps this framework, but you need to kind of encode the rules into a clever specification of the goal set. And this can be done, and this is going to be one of the exercises of the exercise class next. Anyway, so that's what it means for players 1 and 2 to win the play. What's going to be really crucial, so we have the notion of winning a play, but the really crucial thing to consider is, so again, looking at games, what's going to be important is whether or not the player not just wins a casual play as it happens, but has a winning strategy that they can always win. And as I said, I kept that quite informal for the previous game. Now we want to make a precise definition of what it means to have a winning strategy. So that's what we're going to start with after the break. There's a challenge to you. See if you can think for yourselves what the correct definition of a winning strategy would be. Okay, so it's a little bit late, but we'll still have a break till 1:15 because we had a slightly longer break class. Okay. Does anyone have a suggestion what the strategy might be? Or It's fairly intuitive. So a strategy for player one. Well, what does player one need to do? Player one needs to choose numbers. And what information do they have when they make a move? Well, the information they have are all the previous numbers that have appeared in the play. So a strategy is going to be a function. So for player one, it's going to be a function that, given any, so whenever player one moves, there's been an even number of numbers played beforehand. So 0 at the start and 2 before the first move of player one, and the second move of player one, and 4 before the third move. So it's simply going to be a function from even length sequences of numbers to the number that player one chooses when it has seen when that particular play has happened at the previous move. The strategy for one is a function. So we use little sigma for strategies, and so sigma sub one from, well, we can view it as a function from, this is going to be the domain of the function. So its domain is the set of words of natural numbers whose length, so this is the length of the word, is even. And for any such even word, it returns a number, which is the number that player one chooses. So when it's seen n0, n1, n2, n3, this function will choose n4. And the strategy for 2 is similarly a function sigma 2, where in this case we require, when player 2 moves, there have been an odd number of previous numbers played, so the information available is an odd sequence of numbers. So the length, so it's a word of numbers whose length is odd, and again it's simply a function that for any such word selects the next number played by player 2. And then we can talk about a play. So a play of the game is just a sequence of numbers. But we're now going to be interested in plays in which one of the player follows their strategies. Or it could also be a play in which both players follow their strategies. Particularly interested, you have a strategy and you want to consider all the possible plays that you might play with your strategy. So we say a play, that's just a sequence of numbers that follows sigma I, player one strategy, if for all I, we have such the so we're asking the player one's play to follow its strategy. So we want for every even index number it to be obtained by applying the strategy to the previous, to all previous numbers that are there. So this is the play. So every n2 sub I should be obtained by applying sigma of I to the word n0 up to 2i minus 1. Okay. n0, n0, n1, and 1, which is of even length. So in particular, it's the starting move, that's also part of what's given by strategy, is just the strategy applied to the function. Okay. And there's a similar definition of following the strategy for player 2, which is in the notes, but it's the obvious modification for player 2. Its movement is determined at odd positions. So similarly, similar definition of a following a strategy for sigma 2, for player 2. And so then a winning strategy for player 1. Okay. While I'm clearing the board, can anyone define it? So sigma 1, sigma Roman 1, it's called a winning strategy. It's a winning strategy. Yeah. Anyone have an idea?
When we understand possible.
Okay, so how can we formulate that using the definitions? Okay, so we say that every play that follows this strategy lands in the goal set G, player 1. So if for every play, hence the by, that follows strategy sigma 1, we have that play belongs to the first. Okay. So this is a way of saying no matter what the opponent does, because so no matter what the opponent does, we can say that the only way we're constraining the play is that the play is following the strategy for player 1. And in the same way, we define a winning strategy for player 2. There's a similar definition of sigma 2 being a winning strategy for 2. So maybe let's put the let's maybe make the definitions, the modifications in red. So sigma 2 is a winning strategy for player 2. In red, the ready sequence that follows sigma 2. And do we have to modify the last thing? Yeah, but it doesn't fall into G because player 1 is trying to get into G, player 2 is trying to avoid G. Now, let's, at the risk of making things a little bit messy, so this is the definition of winning. Well, actually, maybe let's save the mess for a moment, because we've got the notions of strategies. So now we want the key definitions and the main result of today. So the key definitions now, well, the definition of the strategy, we're going to make some observations, some of which we made already in the context of the perfect set page. So the first observation is it cannot be the case that both player 1 and player 2 have winning strategy. So we talk about a particular strategy being a winning strategy, and we're now concerned with for a game, does a particular player have a winning strategy? So the game is specified by the goal set G. So I'll just call that a game. So for a game, G, specified by the goal set. for a game G, it cannot be the case that both player 1 and player 2 have winning strategy. It's not the case that both, for the same reason we had before, that if they both had winning strategies, play them against each other, and then you get a contradiction. That winning strategy. We say G is determined if one can't be both, but one of them plays 1 and 2 as I've said, the perfect set game can be encoded, as will be done in the exercise class, as a Gale-Stewart game. And for that reason, we know that there are games that are not determined. We say that a game determined if one of the players has a winning strategy. The main theorem today, and this was Gale and Stewart's theorem, is that G, if the goal set G is closed, then G is determined. Who can guess what closed means there? Exactly. So this is finally where we're using this pair space topology that n to the n is a Polish space because it has a metric. We therefore have a notion of open set and closed set. So it's a set that's closed in the limits of Cauchy sequences, and that's what we mean by closed. So this is going to be our main result today, and basically the rest of the lecture is going to be proving this. But just to say that this is a very old theorem and a more recent theorem. So I don't know, this is like 1950s or something like that, or 60s. More recently, but not that much more recently, but I think it's around 1980. There's a big open question for a long time, and it required a very clever proof. This is due to Martin, which is to say that Martin accepts that closed is relaxed to Borel. We know that with the axiom of choice, there exist sets that are not determined, but we can prove that G, that all Borel sets are determined. G is Borel, then G, then. And that's a beautiful proof. It works by transfinite induction. No, sorry, not transfinite, but it involves Beth omega. You remember our large. You remember our when we were looking at strong limit cardinals, the notion of being a strong limit, Beth omega is a strong limit. So Beth omega comes into the proof of Borel. So this theorem is called Borel determinacy. Anyway, we won't get into such complicated things, but today we're going to prove. the Gale-Stewart theorem, insofar as we can fit it into the remaining half an hour, which should be most of it. In order to do this, though, we need to, I didn't really leave enough space, but still I'm going to, so this is now where I'm going to make things a bit messy, like I hinted at before. I actually need to modify this definition of, this is fine for what a winning strategy is, but what's going to be important is we might be midway through the play of the game, and we want to ask, does player one, having got to that point, does player one have a winning strategy from that point onwards? And the same for player two. So let's put this in blue. So a winning strategy, in blue, from W, where W is a word, finite word over the natural numbers. And what this means is that, if this is the word 1, 2, 3, the finite sequence of natural numbers 1, 2, 3, it means player one's first move is 1, player two's first move is 2, and player one's second move is 3. So this is the initial sequence segment of moves. So supposing we've already played this word of moves, does player one have a winning strategy from that point? So if for every play ni, I'll just put extending W. So we only consider those plays for which the first, however many numbers there are in this word, the first that many elements of this sequence are those numbers. Okay? So this sequence has that word as a prefix that follows the player one strategy. From that point onwards, we have this player one attack. Okay, and we have a similar definition for player two. And it's not in the notes, but following the strategy means following the strategy from, you don't concern yourself with what happens on the word W, you just ask about what happens from that. I should clarify that. Right, so how are we going to prove? The main thing to do is now, having made that definition, quite intuitive anyway, I'm going to rub that off, and we want to prove closed determinacy. And as you'll see later in the course, this, and in fact, there's something in the notes about it, but I don't think we'll have time to go to it. These determinacy properties are in fact very, very powerful. So it's good to know statements about how steps of determinants can be very powerful. They require quite, well, we'll see. So I want to prove closed determinacy. So it's quite a proof. So let's start on it. And I'm not going to give every detail, so I'll try and talk you through the main points. So we want to prove that the closed is determined. So suppose our goal set is closed. And what we're going to do is, well, we're basically going to prove that if player two does not have a winning strategy, then player one has a winning strategy. And we're going to do that by defining a strategy for player one and proving that that strategy will be winning if player two does not win the strategy. So we're simply going to define a strategy for player one. we define and this is, we're defining a player one strategy, so we're defining it on even words by, so on at the current state, we've already played this many even numbers as given by the word W. And we define this to be, well, basically, we want to go to, if possible, so we're choosing the next number to append to the end of W. And we don't want to pick any number from which, so that if we play that number, such that player two will have a winning strategy from that point, because that would be a bad thing to do. So let's suppose there exists some number from which player two does not have a winning strategy. And then let's play that number. And just to make it definite, let's play the smallest number. So we play n, where n is the smallest number. Such that 2 does not, this is why we needed the notion of winning strategy from a point, from a play, does not have a winning strategy from Wn. That's the next position we get to with any current position W, current sequence of numbers W, the new number n. So we can do that as long as if such an n exists. So what do we do if no such n exists? Well, if no such n exists, it means whatever number we play, player two has a winning strategy from that point. In which case we're lost because whatever we do, player two will be able to then take over and play their winning strategy. But it doesn't actually matter what we do if such a number doesn't exist. So we simply play zero. Yeah, we give up. But you're not. The rules say you have to keep on playing, not allowed to resign. So we just play zero and we don't resign, but we resign ourselves to our fate. So what we're going to prove is that if player two does not have a winning strategy, then this strategy wins. Not have the winning strategy, then the strategy we've just defined, sigma 1, is a winning strategy for 1. And I'll just say is winning for 1. And then that's clearly enough because that, yes?
Just from a question, when we say who does not have a winning strategy, we mean that they do not have a winning strategy from epsilon, like from the beginning.
Yeah, from beginning, yeah. So here we were in the middle of a play in defining the strategy, but now we're going back to the main argument of proof. So indeed, this is just from the start, and not having a winning strategy is the same as not having a winning strategy from the empty word epsilon. Yeah, very good. So and if we prove that, then we're done. So to do that, suppose 2 does not have a winning strategy. We want to show that this strategy we've defined for player 1 is winning. So in other words, we want to show that any play compatible with that strategy lands in the goal set. So let, and what do I call it? I'll let S be S0, S1, S2, 3, and so on. Sequence of numbers, S for a sequence of numbers. B, any play following the strategy we've defined, and we want to prove, we need to prove that S belongs to the goal strategy. Okay. Right. So to prove that, we start off, so your question was very good, because we start off with assuming that 2 does not have a winning strategy at the start. We're going to show however we play, we'll maintain the property that wherever we get to in this play, we're following our strategy, it will always be the case that 2 does not have a winning strategy from that point on. And you can see we're kind of like maintaining this property here, that we also need to check that that's when we make our moves. We also need to check that player 2 can't manufacture a winning strategy for themselves. We prove by induction of N that player 2, back for all N, player 2, let's keep it Roman, does not have a winning strategy from S0 up to S1. So when n equals 0, this is when n equals 0. This is the empty word. This prefix of, we fix the play that's compatible with an arbitrary play that's compatible with our strategy, and n equals 0, we're just looking at the empty prefix, and by exactly your remark, player 2 does not have a winning strategy. So 2, so this is the empty sequence, 2 does not have a winning strategy by assumption. And for n greater than 0, there are 2 cases depending on whether n is odd or even. Let's do the even case first. No, the odd case first. So when n is odd, we have that Sn is sigma I, and in that case, hang on, no, when n is even, I'm getting confused. If n is, right, we're going up to 0 to the n minus 1, right, so n odd. So in this case, we have S0 to Sn minus 1 is even. It's an even sequence, so it's player 1's move. It's 1's move. So now we consider, so player one is moving according to the function we've defined. So the question is, does there exist a move we can make such that player two does not have a winning strategy from that point? Well, if there didn't, then whatever move we make, player two will have a winning strategy, which means that player two's winning strategy, if we take all those winning strategies from those points onwards and consider them all together, they give us a winning strategy from where we are now, which contradicts that by induction we're maintaining the fact that there is no winning. So the argument goes, and I won't, it's written in detail in the notes, but it's very intuitive. Because player two doesn't have a winning strategy, there has to be, I mean, it's our move that, you know, player two doesn't have a winning strategy from this point onwards. That means there must be something we can do from which player two still won't have a winning strategy. No, the first thing kicks in and player two doesn't have a winning strategy from that point. So, and so here the property holds by the definition of our strategy. And in the case that, yeah, as I say, more details of that argument in the notes, but it's quite intuitive. And if n is even, then it's player two's move. Well, so player two doesn't have a winning, so again, by the inductive argument we're doing, player two doesn't have a winning strategy from the current point we're at, which means whatever number gets played, player two can still not have a winning strategy because player two's move, if there were only one continuation number from which player two would have a winning strategy, player two would choose that and they would have a winning strategy from where we are now. So given that they don't have a winning strategy from where they are now, there can't be any continuation, any winning strategy from any continuation point. So we're fine. So it's player two's move. It's two's move. So since they're just at a high level, since they don't currently have a winning strategy where we are now, there is no continuation from which they have such. But this is preserved by any continuation. Because if it weren't, if they did, as I say, or I've already said, if they did have a winning strategy for one continuation, they would simply choose that, and that would give them a winning strategy from where they are now. Any continuation. Okay, so that's proved this point, this what we were trying to show by induction on now. So now we get to the wrapping up the argument. So we have, so we've got the play that we're looking at, S1, S0, S1, S2, S3, S4, and so on. And we know that at every finite stage in this play, it's not the case that player two has a winning strategy. So, but there is a sequence of winning plays for us with player one, where we'll start off, to begin with, we'll just consider from the starting point of the play. Player two doesn't have a winning strategy. So if player two doesn't have a winning strategy, there exists some play. We're not concerned with following strategies now. There's just necessarily some play that we win, because if player two won all plays, which trivially have a winning strategy, any strategy whatsoever would be winning. So we have So how do I write this in the notes? What's the most? Aha. And let's call this, so here, for some reason, I call this T superscript 0. So we're thinking of this as a full sequence of plays. We have so there exists some. So I'm just explaining to, I won't write everything on the board, but I'm just explaining to you how we get this. We start off from the empty sequence of plays we made here. Player 2 doesn't have some winning strategy, so we're just finding some play, some play for which we win on. We have to win on some play because otherwise player 2 would have a winning strategy. Likewise, once S0 has been played, player 2 still doesn't have a winning strategy, so there is some play that that wins. So some continuation play from 1 onwards that wins for us. Likewise, once S0 and S1 have been played, there's some player 2 still doesn't have a winning strategy, so there is at least some continuation play that wins for us. And keep on like this, S2, and no matter how long a prefix of our play that follows our strategy, we've got our S0, S1 play that follows this play that follows the strategy. Whatever prefix we've got, there's some way of completing it to player 2 from the end of the prefix. Player 2 does not have a winning strategy, so there's some continuation play that wins for us. We have a sequence of winning plays for 1 of this form. Now this, the way we define the metric on their space is that the distance between two sequences is 1 over 2 to the power of n, where n is the smallest index on which they differ. So the distance between these is the smallest index on which they differ is 1. So the distance between, well, they might not differ on 1, but they can't. Sorry, hang on. These might differ on 0, so the distance between these is at most 1. These agree on 0, they might differ on 1, so the distance between them, well, they might agree, but the distance between them is at most a half. The distance between these is at most a quarter. The distance between these is at most an eighth, and so on. So this is a Cauchy sequence. And it's in G, because we were choosing these tails of the sequences to always be in set G, in G. And because this is closed, so since G is closed, its limit also belongs to G. But it's kind of obvious what this limit is going to be. This limit is our play following the sequence, following our strategy, which we wanted to show belongs to G, and we just had. But i.e., our play Si and indeed belongs to G. It's exactly what we want to show, and so we're done. Okay. Right, well, that could be the end, but maybe I'll just squeeze in one tiny little thing. There's a bit more about it in the notes, if I shall, I think, put this in the last lecture of the course. But I just want to mention the thing as a whole. So we've proved that every closed set is determined. I've stated that every Borel set is determined. We've also proved, basically, modulo the reduction from the perfect set game to Gale-Stewart games, that there exist sets that are not determined as long as we have the axiom of choice. What if we don't have the axiom of choice? If we don't have the axiom of choice, then we can't prove that there exist sets not determined. And actually, a very important axiom in set theory is the following. So, without AC, if it's incompatible with AC, we can consider what's called the axiom of determinacy. AC, but no, sorry, AC is the axiom of choice, AD. And the axiom of determinacy says every subset G of n to the n, considered as the goal set for a Gale-Stewart game, is determined. And this is a very powerful and beautiful axiom. It implies that every set has a complex subset. It therefore implies the continuum hypothesis in the form that every set of real numbers, every infinite set of real numbers is either countable or continuum causality. It also implies the negation of the Aleph continuum hypothesis, because the reals are not an Aleph at all. So it's not the case that 2 to the Aleph 0 equals Aleph 1. It also implies the axiom of countable choice. Every set of reals is debate measurable. It has a whole range of powerful consequences. Just using these little games, playing these infinite games on sets, on subsets of aiming for a set in their set. Anyway, so it's a kind of beautiful thing for its consequences. Of course, the big objection to it, well, one, there is several objections one might have. But there's a very obvious conceptual objection to this as an axiom is, axioms are supposed to be capturing some truth about mathematics. In what sense is this, we're saying every set is determined and have a strategy, but where are these coming from? There doesn't seem any reason to accept this. But anyway, having done the notion again, we're in a position to understand the state. Okay, good. Is there any questions? So I shall finish that for today. If you